Should I start? Can I start? All right. So hello, and it's good afternoon now. Nice to see you all. My name is Ali Arshad. I'm associate professor and lead researcher in Riga Technical University. It's in the beautiful country, Riga, Latvia. Today, I'm here to give a guest speech. The title was given to me, very good title, How Can Physics Be Used in Aerospace Engineering? So I guess all of you are physics students. Is that correct? All right. So I will move to my agenda. We're not wasting time. First of all, thank you very much to the organizers for inviting me and giving me opportunity to see you all, talk to you, tell you about Latvia, tell you about what we're doing there, right, and learn from your experience. So agenda is very clear. If you don't understand anything, please ask me. Sometimes I speak words quite weirdly, so, so just stop me and ask. So I'll quickly go. I think you and I deserve to know each other a little bit more. So I'll present my profile. I'll tell you about Latvia and Riga Technical University, my institute, my school where I'm coming from. It's Institute of Aeronautics and Space Engineering. And because it's about students, so I want audience to be the main people we talk about. So for me, focus is you, not me, right? So we're going to go in a way that how I learned from my experience. I'll share with you 5 case studies. My plan was that I'll finish early so we can have a small, short discussion and question answer sessions, right, where you can discuss with me. So I need to rush because we already have wasted few minutes. Different keyboard. So I told you my name already, Ali Arshad, and I finished my PhD in fluid mechanics and aeronautical engineering. It's been quite many years, but still seems like yesterday. You will know one day how it feels like. I'm working in different research projects. There are national fundings and international fundings. Mainly, we work with the Latvian Science Academy, Latvian Ministry of Education and Science. We have European fundings. I'm working with Marie Curie projects. Also, recently I started working with European Space Agency. I've been working with industry constantly. Mainly my industry is UAV and drones. A little bit worked with medicines, and also I worked with, a few years I worked with oil and gas services companies. Research area, aerodynamics, drones, UAVs, CFD, flow control strategies, aircraft propulsion, supersonic high-speed flows, space propulsion. I call it aeronautical engineering. You should call it physics. Am I right? You agree with me? Okay, so just a quick, all of you are physics? Anyone with engineering? Perfect. Which engineering? Oh, good. So, you know, I'm experienced teacher. I know how to engage students. I won't let you sleep. Okay, quickly, Latvia is a very small country. Can you have a look, please? The population is 1.85 millions. It's a country. I checked on internet before coming here. London is 15 million. And it's 1.85. It's a country. So Riga is 1 million. So more than half of the population is living in Riga. So comparatively, if you do a comparative analysis mathematically, so it's a very small scale, right? So our scale is small, so our achievements might be small too, right? We call it home. It's a small island where our campus is located. You can have a look. This is working? No, it's not working. So you can have a look, please. That's the view from the top. And this is the old town of Latvia. When I very first time came to travel, I fell in love with this view. Still, when I drive on that bridge and I feel like, wow, that's the thing, you know, even in winters, can you imagine, full of snow? And that's our beautiful campus. I think next month when you are visiting, so you will have opportunity to see our different laboratories, different institutes. And I don't know how many of you are coming, but I'm expecting a lot of you are coming there, right? So it's an island. We call it Teep Sala. Sala in Latvian language is island. Uh, Fast forward, our university, it's called Riga Technical University. Historically, it was an engineering and technical university. We have four main faculties. I belong to Faculty of Civil and Mechanical Engineering. Then we have, I think is that okay, no? Yeah. So, and then we have few academies which are affiliated with the Riga Technical University. It's Riga Business School and Latvian Maritime Academy. We always welcome foreign students. At the moment, we have more than students from more than 100 countries, and we are expecting more students to join us. We have different programs, including Erasmus and other activities where students can join us for semester or their short visits or for internships. So I hope one of you will someday join us. Okay, because my department is Aeronautical and Space Engineering Institute, I would really love to show you something. So we have study programs, bachelor's, master's, and PhD program in aerospace engineering, in aeronautical engineering, transport system engineering, and we have specific program for the railway engineering too. We have ESA certification, so it's aircraft safety certification. We give the education, we give the courses, we take the exams, and we give certification to aircraft pilots, aircraft mechanics, approved by ESA. We have, because we have bachelor's programs, and historically it was the aviation university long ago. So we have practical training specifically for the bachelor students. So bachelor students, they spend one full semester in laboratories. They do their maintenance engineering courses. They do their hands-on training. And then after this 6 months training, they go to airline. And they spend 4 months there in the airlines, and like they get the basic mechanics training there. We have a few laboratories which are actively working. One of them is Aerospace Engineering Laboratory, where we have UAV development, satellite technologies, CubeSats, and engine testing. Then there is Aerodynamic Research Laboratory, which is mine. There is Acoustic Laboratory and non-destructive testing. We have one special laboratory that below you can see that this is Metamorphose in testing system. So space environment testing we do in this lab. Student teams are working. We have one active student rocket team, which is supported by the ESA. We are always engaged with industry, with schools, with public. And this is last year in Riga was Drone Summit. So there were delegation from many European countries, and they came to my lab and office, and that's me. After this picture, I came to know that I have lost a lot of hair. So, so we are always engaged with industry. Okay, wanted to rush with that. Let's move to the topic. So topic is, how can physics be used in aerospace engineering? If I say for a moment, I don't know, what would you say then? Can we use it? Well, I would say it's not about using. I would say aerospace and aeronautical engineering is physics. So there is no question of using it. You know, in my opinion, aircraft or spacecraft, aerospace, it's applied physics. We don't do anything new. We just apply and understand the physics, right? But because of my personal ideas, I want to change the topic, if you would allow me. How can physics and mathematics be used in aerospace engineering? Because physics is something physical, right? But how would you define it? The language in which you define the physics is mathematics, right? So they go hand in hand together. Without them, Separating them is not possible. So my idea is that I will show you my personal perspective, uh, what I have learned over the years. Around more than 20 years ago, I joined as a bachelor student, and now I'm teaching. So it's a long time. What I learned, a lot of things, good experiences, bad experiences, uh, but here I chose 5 case studies, not to show that how good everything is, but to show how challenging sometimes things can be. And as young students, you might come across with these challenges, right? So I don't say that we tackled it very good or I did it very in good ways, but at least you have one case study from me to understand that how you could do how you can do better in future, right? So ready with me so far? Any question about Latvia or no? Good. First case study, that is UAV design. That's the current UAV we are working on. It's a small scale UAV, just 1 meter wingspan, right? 1.3 meters wingspan. So current system we are working on, we are developing, and we are designing it. Now, it's a very beautiful picture, and I really like it. That's why I put it in this presentation. In our university, it's called Aerospace Aerodynamics. It's a bit of argument because aerospace, space, there is no air, so, but aerospace means aeronautical and space engineering, so computational fluid dynamics. Do you know why I love this picture? Uh, do you like it? Really? You know why I love it? It's beautiful because it's extraordinary bad design. That's why I love it. If you have a look, it's complete flow breakdown. The UAV is not flying really good. You see the vortices on the vortices on the wing body, on the surface of the wing, right? That actually correspond to stalling and drag. So the problem is this. Look at the tail section, right? Then the joint, fuselage, and the wing section. And look at the tip section. So tip flow is like spilling away. Aerodynamics, fluid dynamics is about to control the flow over the surfaces, right? But we are not really controlling it. So what goes, how to solve it? Yeah, see, I'm not letting you sleep. So how to solve it? What do you think? Imagine you have graduated and now you are working as an engineer or scientist. What should be the what should be your approach? What to do now? Hire someone? Please. Yeah, excellent. Exactly. So here, I'm not thinking here in front of you as an expert. For me, I'm just another student like you. Older, of course, but but it's like student to student talk going on. Agree? Deal? Yeah. So my plan was this. We developed the concept, right? What should be the design? Because when you talk about aircraft or spacecraft, that is defined by the mission. What is the mission? High speed, low altitude, high altitude, right? Payload, what exactly you want, right? So once you understand the mission, then you design the concept. Concept design means that you do the mathematical modeling, right? For improvement. Now, what is known to us? Known to us is that we have a terrible design. We know the mission, we designed it up. We thought it works, but when you did the simulations, you did the testing, it's not working. So concept after, once you have developed the mathematical design, next simulate it, right? To CFD simulations. Then we have to make the design optimization. You might make very good wings, but they are not good integrating with the rest of the airframe. Is it a good idea? No. So optimization, when we use the word optimization in engineering, it doesn't mean the best, it means the appropriate. right? Because you compromise. Engineering is about compromising. Okay, then we move to experimental testing. Never fly your airplane without testing, or your UAVs. No, even if you have perfect simulation. I was reading somewhere that uh, there is not a single flight test which was performed without wind tunnel testing, experimental testing. And finally, we do the flight testing and we develop the prototype. What is after prototype? Uh, in university, we don't really care to sell it or no. It depends, right? Our job is done. So we prototype it and we test it. So for mathematical modeling, first, solution. The problem was that wings were not producing enough lift and the drag coefficient was very high. How we solved it? We developed a program, we developed a code to optimize the aerodynamic performance of airfoil. Now, a wing is a three-dimensional body, and airfoil is a two-dimensional body. So why we went to the two-dimensional? Because to deal the three-dimensional turbulence is very difficult, right? So you go to two-dimensional model. Sometimes mathematically we go into one-dimensional model. For example, if you have a nonlinear system, right, you need to linearize it. 3D linearization, it's terrible, right? So go to two dimensions, then one dimension. Same came to my mind, not my mind, it's classical way of doing. So we tried to improve the performance, aerodynamic performance of the wing at the airfoil level. In red color, you see the original airfoil we used, uh, 6043, the series, right? And blue color, you see it is the improved, optimized version, right? That fixed the problems that we faced for the performance. Now, this is not enough. So work was pretty good. In one slide, what you see, we spent 2 years. Really, me and my team, we were working for 2 years. Of course, because we are from academics, we must publish it. So we published this work. So now we understood that aerodynamic surfaces, we have developed a method so we can improve the performance, right? Or you can say that you decrease the losses in another way. Next, spillage from the the wingtips displace. So there was a flow spillage. So if you add the active flow control system, you need outside power source. You need to run it. So there is a very good technique. It's called passive flow control. We use on Formula One cars, and UAVs very much famous these days. The problem is that most of the aerodynamists, they didn't believe that at such a small scale, 1.2 meter wingspan, probably the winglets or wingtip devices, they will not really work. We understood it, but we thought, okay, let's give it a shot. So we started to do it. We started to repeat. We saw different aircraft design. Airbus calls it sharklets. So we just took the Airbus design and put it on our small drone system, and you see, we just simply call it with the classical name, the blended wing, the blended winglets, right? So on the left side, there is the wing without the winglet, right? You see the vortex, it's quite huge vortex. So what happens? That vortex offers drag, right? Performance drop. If you have this winglet, because you are controlling the wingtip flow, so what happens, this vortex is now like breaking down into very small vortex. So the resistance to the flow is now smaller. In that case, we improved the performance. So actually, the optimization of the airfoil gave us higher lift, but designing the winglets helped us with the drag properties, right? Together, hand in hand. Based on this, we developed different variants of UAV system for different missions, right? So here you can see that for one specific low speed, low altitude mission, we have 3 different variants, right? It depends. So that was one of the method. improvement. Next, we went for prototyping. So what happens? We make a very bad prototype because we know that once we fly, it will break off. Right? So we break it many times unless and until we know the final airframe structure. So that was the initial prototype, right? Then we went for wind tunnel testing. If you can have a look, that it's not very clear here. On my screen, it's pretty much clear that you scale down the UAVs and drones, right, and test in the wind tunnel. We were just there. So after testing, we developed the prototypes, and then we did the real flight tests. Based on this research, now we are working on different UAV systems, right? One of them is this VTOL system. So in university, we did concept designing, we did the simulations, we did the optimization, testing, and prototype. What's next? Product development, right? That depends if any company wants to work on your systems. So what happens in our case, companies are not really doing or taking these drones, but they are asking us to improve their systems based on what we learned here, right? So that is my main idea, that there should be always, we should always, cover the gap between industry and academia. So we found solution. I don't know if you agree or no, but many people don't agree that university is not to develop the product. University is to develop the technology, right? Which can be useful to hundreds of products. That's what we did. Okay, what exactly we did? Aerospace aerodynamics, but if you go deep down, we tried to understand the flow physics. So was I working on physics? Exactly. So if any one of you will go and work in aeronautical engineering, so what you're going to deal is you're simply defining or applying the physics. Isn't it flow physics? How we defined it by mathematical modeling. So case study number 1, what do you think? Physics is important? Yes. Now back to my young times, not long ago. Personal perspective, why I thought of this solution, because we had a very bad design. When I was in university times, I was working in laboratory voluntarily as a volunteer. Quite stupid, right? And there I worked on these delta wings. I did some wind tunnel testing, and I got very strange results. I was just talking there, the same results. And there I learned it, that if you control the vortex, you can actually change the lift characteristics of all UAV system. Because I learned it as a bachelor student 20 years ago, I still was able to define it. I still was able to solve my problems today. Right? And because I solved my problem, now me and my team, we can offer help to so many other products. Right? So that's the idea. Science, research, it's a collective business. Knowledge belongs to everybody. Right? Okay, that was my case study 1. Hope you agree. That's physics. Trust me. Can we move to second one now? So when I started my master's degree, I went to my professor and I said, I'm not sure which topic to take. And he told me, how about micro gas turbine engines? I had no idea what he's talking about. I just took it. And when I started to do it, and I realized that that was a big mistake. What was the problem? It's the demonstration. It's not the gas turbine engine. But exactly this is how it works. Imagine aircraft engine on this finger. Micro gas turbine engine. So turbine diameter was 8 millimeters. Like quarter of an inch, right? So 8 millimeter whole turbine, right? So the idea was that if you scale down a flying machine, so what? First, it was thought that the problem is unavailability of technology. It's like MEMS system were not so developed, micro machining was not so developed. Now it's possible, okay, let's scale down aircraft, maybe a mosquito size, right? Or a bird, like biomimicry, very famous topic in aerodynamics. So, but things were not working. You can see this plot. So the performance in green curve, can you see the colors there? Yeah. So high performance here, right? And when you scale it down, you have low performance, right? I call it failure. So system is failing. Failure is success. That's the topic. Do you agree with me that failure is success? Right. So there is a significant performance drop of the microcompressor when you scale it down because of the heat. We didn't know this before, right? So what happened? My job was to figure out why we fail, right? So I spent 2.5 years. It was quite difficult, trust me. I spent a lot of time because I was young, and you know, when you're young, you have energy and you're more ambitious. So I was ambitious and I was into this. I wanted to understand what's happening. Turned out to be that turbine and compressor, they were mounted on the same shaft. So there was induction heat transfer. Because of that heat transfer, the performance was dropped because heat energy and flow energy, flow physics and heat physics, they were interacting with each other. Why? Can you give me the answer? Aerodynamics was interacting with heat. Heat transfer depends on coefficients, right? And area, surface area. And aerodynamic forces depend on coefficients and surface areas. You decrease the surface area significantly, right? It's kinetic energy, right? And it's heat energy. This interaction, well, you can see bad results. What exactly was happening, we wanted to understand the physics. Have you seen? Well, I have never caught so beautiful vortex later in my life through simulations. So it's a special type of vortex, which is tornado type vortex, that emerges from the base plate and goes up over the span, right? With heat transfer, what is increasing here? Your system is getting more entropy. We don't like entropy, right? Overall effect, look at this. Performance drop with heat energy, performance drop 35% and pressure ratio drop 24%. So you're losing 35% of performance. Is it worth? No. So once we know, if you go deep inside, this is heat energy transport equation, right? This is turbulence equation, RNG models, and this is simple heat induction. I made a model, based on this model, I add this into the simulations, we got the result, and what we got, actually we didn't know physics. Agree with me? Thermodynamics, do you call it physics? Right? It is a very important type of physics. Okay, next, let's move. So, I'm so happy to say my master's degree was proving a failure. Such a loser, no? So I proved the failure and I got the master's degree. So my idea is that science is about exploration. Don't rush for success. Don't rush, please. If you're going to be engineers and scientists, patience and explore, investigate, right? Don't waste time. Case study 3, jet engine instability. It's so complicated phenomena for so many years, decades passed. So now I'm in my PhD. Right? I don't want to remember this time, it was so difficult. So, so what happens when we have engine failure, right? It's called surge and rotating stall. Rotating stall, there's a stall cell that rotates with compressor. and that blocks the engine, and then boop, possibly. So you need to recover. You always have stall margin when you fly on that. So when you do experimental testing, the data is lost in filtering. So I wanted to make the stall detection on raw filtered or raw data, unfiltered data, right? So I worked on a modeling. I did some mathematical modeling. I used at that time analytic wavelet transform. 15 years past, I don't remember much now. But anyway, I was working a lot. And then I did experiments. What happens that fighter jets, when they make maneuvers, these maneuvers, the air inlet angles change, and compressors are designed on fixed angles. In that case, it's called distortion, and that creates stall, two types of stall, one spike or the model type of stuff. Now, how to bring this in laboratory? Do we have fighter jet? No, we have just small compressor.
Could you put the model engine on a pivot in the wind tunnel and just change the incidence?
Well, yes, you can, but go for cheaper version. That's very expensive. You know what I did? I just put the screen there. So you just put a screen, random screen rough, put in front of the compressor, and when you run the compressor, air changes angles. So you are doing in laboratory, actually not flying, but you make the conditions which happen, the same condition which cause the compressor failure. So I did this. We figured out a lot of things, but we figured out that it was not from the tip of the compressor, right? So these are the tips, right? That part, it was not the tip, but actually it was the base section, the hub section of the compressor. So when there is different angle air entering into the compressor, from the base there is a low pressure zone that creates a vortex. That vortex goes up span wise and blocks the tip. When tip is blocked, that's what we hate. So engine goes to stall. So my job was what I needed to figure out the mechanism. We don't know yet. Still, we don't know. But, well, I tried to give one of the explanation. So when I was in my university, people had many questions. I came to England. I met Cambridge professor, Professor Day. Now he's retired. And he said, excellent work. And after that, everyone in my university was happy. Okay, now it's approved. So, actually what I understood, it was momentum shift due to non-uniform pressure difference. Momentum shift. Am I talking physics? Am I talking Newton's second law? Do you think there is a use of physics in aircraft engines? There you go. I'm the example. I suffered. Okay, there you go. What I did for my PhD, complex mathematical modeling, experimental fluid dynamics, computational fluid dynamics, signal processing, nonlinear comparative analysis, loading, you name it. You know what it is? Theoretical physics, you love it, right? As I heard. Fluid dynamics, piezoelectricity, right? You're playing with pressure, solid state physics, classical physics, and a little bit of aeroelasticity. And then I ran away because I got my PhD. Case study number, so moral of the story, I got PhD. Case study number 4, sports aerodynamics. I was so excited that we started in Latvia the sports project. I thought that will be easy. Turned out to be, we know how aircraft and helicopters fly, but we don't know how aerodynamics of sports work. So aerodynamic is divided into like flight aerodynamics and ground aerodynamics. Ground aerodynamics, bridges, buildings, sports aerodynamics. So we are working with Latvian national teams. You know what is the most important in sports aerodynamics? That thing. Drag coefficient, okay, density is not changing, velocity, let's say it's fixed. Coefficient of drag, we can't really work on it. So what's left? Area. So here, the luge sport, what you see, you can't change human body. That offers drag, right? So, but can you optimize the body maybe with gestures? So we figured out that athletes, they had problem with their shoulders. When they were, how to call it, like curving their shoulders like this, they were producing drag force here. I don't say this was the only reason, one of the million of reasons, right? So we worked on this. This is Latvian national team there. So for them, they're so beautiful. For us, these are these. So we do 3D scanning and we simulate them. You see the pressure points? Look at the doubles one. 1, 2, 3, 4, 5, 6, 7. We know the problems. That's more than enough sometimes. We don't know solution. But single solution we fixed. You see, drag reduced. So we went to Germany, we performed full-scale wind tunnel testing. The results showed that the mathematical and simulation models we developed, they were up to 95% accurate, what we did the full-scale testing. Result, don't spend money. So now, that's the A4 size paper. I make different gestures, we scan, and then we make the small models, and we will test in small scale wind tunnel exactly the way we did other things. So, student formula team, they came to us that, hey, you are the head of aerodynamics and aerospace. Yes, can you design a wing for our student formula car? You know what I said? No, I don't know. How can I design? Really, we had no idea. So we little bit helped them. Again, in student formula, DRS system is not allowed. You cannot actively control, but you can passively. So we needed to design. So what happened? I took the drone UAV wing, flipped it, optimized it, and gave them. So initially they're saying results are good, problems are in manufacturing, but we are hoping simulations say that they are really good. This is bachelor student work. She was working on passive flow control devices of Formula One helmets. Because in Formula One, professional Formula One, not student one, so the inlet of the engine is just behind your back, right? So if the vortex flow goes into the engine, performance drops. There is theory. Don't know much. For bachelors, it was enough. That's the result. Literally, we spent years, thousands of simulations. Literally, thousands of simulations. And last month, Alina, Latvian athlete, she won the silver medal in luge. It was so happy moment. Actually, we wanted to cry, but we were so happy we couldn't cry. So, what I want to tell you, science is about patience and innovation. It's not about invention anymore. It's innovation, right? Please, as youngsters, never forget. We are working on e-sales, case study 5, because I'm heading the department, so it's under my department, not my direct field. So the idea is that propellantless propulsion for deep space missions. Do you believe it? Hard to believe, right? So, there's solar cloud, solar weather, what's it called? Solar cloud. So when the charge particles run away from the solar environment, right, and they reach to planet's environment. So what happens if there is a small spacecraft? There is a tether. Am I using the right word? That the shaft very thin, right? You emit the electrons, and this shaft is positively charged. So the protons from the solar cloud, they repel each other. This repulsion produces a pressure zone, and it will propel on that side, thrust side, right? So you have same charges and propulsion. Again, same charge, propulsion. So you don't need fuel, right? It's very slow, but it's concept. This concept we are developing along with 12 organizations throughout the Europe. 2 PhD students will be there. The name of the project is e-sailors. So I'll be heading two PhD students. We are developing and working. So our job is to give, again, mathematical modeling and simulations, right, and animation. That's the whole concept. We get the solar cloud, right? We launch it into the LEO, and then slowly it will go beyond, right? That's the overall concept for deep space missions. So back to the point, this e-sailor propellantless propulsion in aerospace, everything is physics. You know what it is? I think it's Newton's third law. So that's my summary. Physics of universe is written in mathematics. Future aerospace challenges won't be resolved in a factory. Someone like you, youngsters, one day have to resolve it. You will have to resolve it, right? What you're learning today, it's not waste. Don't ever. I also thought in my life when I was young, oh, maybe I will not use it when I will work, but actually everything does matter, right? This is my saying, trust me, I didn't steal it from internet, that success in science is hidden in very small details. So please believe in the fundamental knowledge what you're learning at bachelor's level, right? It will really help you. I don't say I'm one of the successful scientists, but I want to say that I wish I'm one of the successful students, right? Uh, Today's learning is key to future. Please think of innovation. Don't run for inventions. It comes with innovation. It comes with, you know, beauty comes with pain. Science comes with innovations. So that's it on my side. I tried to cover it as soon as possible. Uh, a bit of too much, but I wanted to share everything with you. So, conclusion: are physics and mathematics important at the university stage? It's your decision. I think the question is not correct because physics and mathematics are everything. So airplane does nothing. It just uses the physics. It's applied. So aerodynamics, aircraft, spacecraft, space engineering, it's actually applying field. Right? Thank you. Let's move to discussion. Any question? I love when students checked. It's a subject study as athletes because they have physical and mental stress, right? So for that they were applying for fundings, and then it became not only sports medicine but sports technology. Then we jumped in. So in that case, I remember I was with national team coach and we were scanning these athletes, and he got a call from ministry that you were talking about some technology and science. Your scientists, where are they? What they're doing? They wanted to meet us. So we got a call that one medicine university is working on their medicine research, right? And you talked about technology. How about we join this? So this VPP, it's Latvian word. VPP, it's like in English, it's National Research Program. It's a national level program that integrates many fields. So we are part of one big field, technology. They call it technology in Latvia, so sports technology. And I'm heading the team sports aerodynamics. So there are 4 teams working: materials, tribology, sensors, and aerodynamics. So it's a tiny bit of part. So we made joke that aerodynamics gave 1%, materials gave 1%, and tribology gave 1%. 3% of this Latvian silver medal belongs to us. So they say, yeah, that's true, and then they say it belongs to our university. So it's a mix of the game. They reach to us, we reach to them together. I hope I answered. Yeah. Any other question? Any other thing to talk, please?
I have a question. Out of the projects that you studied over the course of when you started to now, which projects gave you like the most insight that you feel stood out most to you?
You mean among these case studies, or when I was as a student?
Not just the case studies, but pretty much everything. Like, what kind of things stood out to you most when, like, what taught you the most impactful thing?
To be very honest, rejection. Because Because when I was in masters and PhD, we needed to publish our work and get approval from the board of professors, and they would always reject. So I remember my PhD proposal was 3 times rejected, and then I got habitual. Doesn't matter anymore. So that was very useful. I mean, in science, rejection is very important for us. It teaches you, and that teaches you patience, and then you just don't give up. And when things start to work, you don't even feel how it happens. So I think when I was failing, because what you see in 1 hour, it's like it's 20 years probably. Like, I don't know, but yes, that was the big for me. Rejection taught me a lot. Failures taught a lot, and we will learn again. Let's get more 100 failures. Who cares now? So we'll get more failures. We'll learn more, right? That was my, how you go, like that was my spike, or spark. Sorry, spike was that engine. Yeah, we go with you first.
Just out of sheer curiosity, if you could jump into another field, what would it be?
Because I'm Asian, my father was doctor. Sorry, so he wanted me to be a doctor. Many of my like family members, they are, so, uh, you can switch a field in a way that I did my bachelor's in it was a joke. Please don't take it serious. Yeah, I did my bachelor's in mechanical engineering, and then I worked 2 years as a mechanical engineer. And there I realized that I want application engineering. Really, I was like, okay, inspection, temperatures is enough. And I wanted, but when I went to application engineering, I realized that that is nothing without research. Then I decided to go to research side. So it was transition. See, from mechanical engineering to industry. I was about to get promotions when I left. My friends were like mad at me that maybe I have some psychological problems or what. So that was so transition is very easy within scientific field. I think, yeah. Do you believe that transition is easy? I believe that, again, maths and physics. If you know this, you can have your transitions easily. Yeah, Ziad.
So, out of all your failures, which one would you say sort of inspired you for your biggest successes?
Uh, the work what I was doing with raw data, because without filtering, it's pretty much uncommon. People usually don't do, and I was not able to fix it for 7 8 months. And I remember our university was going to beach trip because summer came, and I gave up. I think I should stop it. We came back from vacation, all our group, research group, and I remember the very first day I was sitting. I don't know what happened, and I solved it. So then I realized that it's like true, something we see things maybe on internet that okay, you don't give up. Things just happen. Too. I can't crack it yet. I mean, why I couldn't fix it for months, and when I came back and suddenly I saw, oh, it's done. You know what I did the next? Immediately wrote an article and published it. Yeah, I need it for my PhD. So I'm trying to make you in a way like a youngster should understand how it feels. Any other questions? All good. So, what is the outcome of this lecture? You will study good, right? Okay, that's it then, right? Thank you very much. I'm so happy to meet you all. Good luck.